atomic physics review, and I'm reviewing like all of the concepts that we did in the course or in the unit. The questions that we're going to review after are diploma questions. So I want to stress that that's not the kind well, you're not getting multiple choice questions tomorrow. You're still getting written numerical response, but we're going to practice some multiple choice because this is also diploma review atomic physics. I'm not going to come back to it. So the first 4 pages is just all of the kind of concepts and formulas from the unit. Which it's a big unit, but actually I thought that when I put it all on 4 pieces of paper, it actually seemed kind of concise and not that much material. It's all very similar stuff. So just some common mistakes that happen on the diploma exam is when using the half-life formula, N is the amount of material remaining. Okay, N, the amount of material remaining there is N, and so some students use N to be the amount of material that you start with, and NO to be what's remaining, if they flip them. So that's a common mistake that they found. The other thing you want to remember is, NO will equal 100% or 1 if you're given, what percent is left. Oh, did I not give it to you? No. Apparently I didn't hand it out. Okay, there we go. Sorry. My fault. To waste more time on the video. So this, if this uploading videos to YouTube works, it's going to be interesting, I think. Anyway, okay. When writing beta decay, remember there's beta negative, beta positive, and to pay attention to what it's asking for. It should state beta negative or beta positive or electron positron, because that's what's going on there. So the beta negative is an electron. Beta positive is a positron or an anti-electron. And so then no one used to be able to use the term positron. The other thing to remember about beta decay is the antineutrinos and the neutrinos. Most of you are remembering that, but there's a couple that are forgetting the neutrinos and the antineutrinos. So the antineutrino is a V with a line over it, and the neutrino is just a V. So that was really kind of only the notes that they have, the only notes they have about this particular unit, how the questions are done. I guess actually another note they have is that students recognize each of the models of the atom, but have a hard time kind of with the whole through line of the models, like looking at the models sort of a general thing, like in why certain models were rejected in favor of newer models. So that's sort of the first thing that we talked about, was like the evolution of the model of the atom. So you need to kind of have a working knowledge of what the models are. You need to know who was involved, if somebody was involved, and why each one was rejected in favor of the next one. So these are pretty much the models we did, except I forgot, I didn't want this to be standard model, I want that to be quantum model, because that's what we did there. The standard model comes after. So the billiard ball model is Dalton, and that was the one that had been in place for hundreds of years, really, or about 150 years or so before it was rejected. And it just basically said the atom is indivisible. The atom is the smallest piece, right? So it said the atom is the smallest form of matter. Its limitation was really that things like the fact that atoms of elements can combine to form compounds suggested there was an internal structure for the atom. Like it suggested that the atom wasn't the smallest. So formation of compounds. Suggested an internal structure. Raisenbund model is Thomson. Okay, and Thomson is responsible, like he discovered the electron using cathodes. And so that Raisenbund model is that the atom is sort of a bunch of electrons embedded in negative goo. positively. Okay, so electrons embedded in positive Q. Yes, we didn't really discuss, and there weren't any sort of recognized limitations to that model. It was more just that people kept working with trying to refine the model, make it better. And so next in the line is Rutherford, who has the planetary model. Right? And he discovered the nucleus using gold foil and alpha particles. And the limitation for him, planetary model is that small, dense, positive nucleus with most of the mass, and then electrons orbit the nucleus. The limitation here is that it contradicted Maxwell's EMR theory. Which from your unit assignment or the quiz, I guess it was the quiz, really, nobody got that question wrong. Like you guys all have a handle on that, but that's the limitation for Rutherford. And that's good actually, because that's, well, but for some reason all that kind of reading right out of the book, like some of that knowledge stuff, like is the stuff that is done worse on the diploma than on the calculation stuff. Yes, I know. I know. But you'll remember it now. Okay. Bohr model is obviously Bohr. And he said that the electrons orbit in discrete energy levels. And so he said that the radii are quantized, and the energy levels are quantized. Writing very well. And the limitations of his model the numbers only worked for hydrogen, and couldn't explain why the energy levels were quantized. I'm just going to pause the video and okay. And then the quantum model, there's no real one person associated with the quantum model. I wrote down de Broglie because of the electron wavelength. So electrons as waves. And Heisenberg because of his uncertainty principle. Okay, and so then what that quantum model said was that the electron orbits as a wave. Which, and what was said about it was that the circumference had to equal a whole number of wavelengths. And that was why those energy levels were then quantized, and why the radii were quantized. They only happen at certain spots. They had to be whole number multiples of the radii. And the uncertainty principle just says that you can't know the position and velocity at the same time. Knowing one changes the other. So along with knowing each individual model, you need to know that there is this evolution of the model of the atom, and that models are just something that we use to make the descriptions more convenient, to help ourselves understand things. They don't actually exist in reality. It's just a model. Fields are just a model. They're not, well, unless you believe in string theory, but fields are just, again, this is another example of a model. So models are things that change. They can, as more is learned in physics, the models change, which is evidenced by this evolution of the model of the atom. Same thing with model of light and EMR, which we'll talk about next week. Okay, you guys okay with that? Okay. So then we get into the formula stuff, which is, for some of you, is a little bit nicer. So Thomson discovered the electron using cathode rays. So one thing I want you need to remember is that cathode rays are electrons. And so he, he used cathode rays and he put them in a magnetic field so that they were deflected by the magnetic field, and then he used that to discover the charge to mass ratio of the electron. So if F equals Fm, then mv squared over r equals qvb, and then you can solve for different variables in there, or the charge to mass ratio. And then, of course, to find the charge to mass ratio of a particle, just take the charge and divide it by the mass. He also balanced electric and magnetic fields so that the charge, so the cathode ray went straight through undeflected, and that allowed him to find the speed. Electric force is charge times electric field, and magnetic force is QVB. Of course, cancel the charges, and then that's basically used to determine the velocity of the cathode rays. And so he used that to find the velocity, which then he could substitute into this formula and find the charge to mass ratio. After that, we don't talk about it, like I didn't teach it in this unit, I taught it in forces and fields, but basically Millikan, with his oil drop experiment, which I'll just mention here, but it's not in your test tomorrow, found the elementary charge. Okay, so then we talked about spectroscopy. So we talked about the three types of spectra, and generally this question was done, for the most part, like you got, most people got about half of the information I wanted in there on the question on the unit quiz. So I wanted a description of each spectrum. So that would be that a continuous spectrum is all the colors with no gaps. An emission spectrum is mostly dark with colored lines at specific wavelengths. An absorption spectrum is a continuous spectrum with dark lines at specific wavelengths. When I said related to the Bohr model of the atom, it's this and this that are from the Bohr model. It's how Bohr explained they actually happen, which was by electron transitions. So an emission spectrum is when an electron goes from a higher energy level down to a lower energy level. Okay, so it emits energy because it's losing energy, right? It needs more energy to be in a higher level. If these are sort of our energy levels here, and this is A, B, C, D. This is the ground state. It needs less energy to be here than it needs to be here. So if it goes down there, if it goes that way, it's emitting. So it's an emission spectrum. If it goes the opposite way, it's an absorption spectrum. Because it has to absorb energy from some way to get up there. So to absorb that energy, it can absorb it from two places. I might be getting ahead of myself. I think I have this. No, I don't. It can absorb energy from either light, and in that case, it has to be the exact amount, or it can absorb it from an incident electron. And what that means is some sort of incident electron comes along, collides with the electron in the ground state, passes some of its energy to that electron in the ground state, which then allows that electron to move up energy levels, and then the incident electron, carries away whatever energy is left over in the form of kinetic energy. And then that electron that's absorbed the energy to move up is eventually going to move back down again and emit energy. So then I kind of talked about this, the electron transitions. Electron in the ground state can absorb energy and move to outer levels, can get energy from light, where it must be the exact amount, or from incident electrons, and that describes it. And then if you're trying to find the wavelength or the frequency of light that's emitted or absorbed, you're just using the formulas from the quantum model unit. So it's E equals HF or E equals HC over lambda. Okay, so then into kind of nuclear stuff. This is sort of the nuclear physics stuff. That other stuff is atomic physics. This is what we call nuclear, because now we're getting into looking at just the nucleus. The other stuff was looking at the atom. So mass defect, just remember, it's the difference between the total mass of nucleons and the actual mass of the nucleus. So that's delta M, and it's the mass of the nucleon. So mass basically of neutrons mass of nucleons minus mass of nucleus, remembering that the mass of the nucleons is mass of protons plus mass of neutrons. And if you're given the mass in the question, use those masses, otherwise use the constants from your formula sheet. Isotope notation, atomic mass number, element symbol. Z equals the number of protons, and it's the number from the periodic table. And then just our different types of decay: alpha, beta negative decay, beta positive decay, and gamma decay. So just I had examples here that I could do for you for that. So the principle that you're using when you do radioactive decay is physics principle 8. Was that right? Physics principle 8, which is conservation of nucleons. That's really the only principle being used here. So alpha decay, you go 2 to the left on the periodic table. Beta negative decay, basically what's happening is a neutron turns itself into a proton and an electron, and the proton is added to the atom, like is kept in the nucleus, and the electron is expelled. For this one, if we have 14,6 carbon, we get rid of a beta particle. The beta particle, which is basically an electron, so you can write it as an electron or as a B for beta. We add 1 to the bottom number. So the top number, A, stays the same. Z gets 1 bigger, and so then you're moving 1 to the right on the periodic table, and then you have to remember your antineutrino for beta negative. Beta positive, that's 8 for beryllium. Beta positive is when a proton becomes a neutron and a positron, or positive electron. The neutron is kept, and then the positron is expelled. I guess actually, like in these ones, like you're doing conservation of nucleons, really in beta positive and beta negative, you're also doing conservation of charge. because what's happening is, that neutron, which is neutral, becomes a positive and a negative, which keeps the neutral charge. Proton, which is positive, becomes a neutral and a positive, which again keeps the positive charge. The conservation of charge is physics principle 7. Of course, those are on your formula sheet. You don't have to remember what principle is what, but you need to be able to use it. So we have 0, 1 beta, beta positive. So then our bottom number is 1 less. So we have 8, 3 lithium plus a neutrino. And then gamma decay doesn't change anything. It's just when the nucleus emits a high energy gamma photon. And it's almost always accompanies one of the other types of decay, and you just add this symbol in, the 0, 0, and the funny shaped Y at the end, in one equation. Like in one writing the equation. We don't want to write a whole bunch of different equations. It tells you to write 3 or 4 equations. So then you need to know decay change. And decay change, there's a couple examples. There's one in the textbook, and then there was one in your practice booklet to work on, where just that's when an element undergoes many decays before it reaches something a little bit more stable. And determine the type of radiation by deflection and magnetic field. So you had a question like that on the quiz. So that's using your hand rules. And you want to be careful. A couple people on the quiz had a beta negative and alpha going the same way. So you had a negative particle and a positive particle deflecting the same way, which can happen, right? You need to have all your positive deflecting one way and your negative deflecting the other way. Half-life, I already kind of mentioned the thing about using percents. So just remember that this is the way the formula is on your formula sheet. And so you want to remember that n is the time over the half-life. And then how to read a decay graph. So how to find half-life from a graph. Okay. 22 minutes already? Oh boy. That's a long video. Okay. Fission and fusion. The thing that is common between them is they both release massive amounts of energy. Fission is in a CANDU reactor or nuclear power plant. Fusion is in the sun. Not successfully, not in any good way. They can do fusion where it takes way more input energy than output energy. They have done it, but no, I wouldn't call it successful. And so then what fusion is fusing or joining two smaller atoms. And fission is splitting the atom. The waste product is radioactive. For fission. For fusion, waste is not radioactive. So that's one of the other sort of justifications for working with fusion is the waste products aren't radioactive at all. Basically water, I think is one. Mass energy equivalent to nuclear energy release binding energy, so delta equals delta mc squared, which just says that mass and energy are the same thing. And there's a physics principle for conservation of mass energy. It's physics principle 6. In terms of a fission and fusion reaction, delta M is just the mass of the reactants minus the mass of the products. You need to know what happens when antimatter and matter collide, they annihilate each other. and 2 gamma ray photons are emitted, and you need to know that that's based on conservation of momentum. Which is physics principle 4. Fundamental forces and your mediating particles. So strong nuclear, which is the gluon is the mediating particle. Electromagnetic, photon is the mediating particle. The weak nuclear, which is the weak gauge bosons are the mediating particle, and then the gravitational field, or gravitational force, and the graviton is the mediating particle. Graviton being the other one that hasn't really been seen or witnessed indirectly.
What are the strong bosons?
No idea. No idea. Couldn't answer that. Interesting question, though. I don't know that there are any. I don't know why they're called weak gauge bosons. I don't know what the gauge is in there for. I think it's just an odd term, but. Know what antimatter is. Have an idea of cloud chambers or bubble chambers, like, and how to analyze particle tracks in those. What particle accelerators are, and basically, like, the mathematical analysis of particle accelerators tend to use is the F equals FM. When those questions come up, it's usually the F equals FM. Because what happens in a particle accelerator, or like a mass spectrometer, kind of similar stuff, is that they accelerate kind of particles and then expose them to a magnetic field, and so certain types of particles will deflect in certain radii. So if they have a detector at the radii that they're supposed to deflect at, then they can tell what the particle is. Subatomic particle zoo, really you need to kind of know quarks. So know that a proton is up, up, down, and a neutron is up, down, down, and how to analyze that with the charges from the formula sheet. And that was the notes we did. And then just a few other things in there that electrons are leptons. Like, there's all these kind of different names for the families of particles. So leptons include electrons and the electron, you know, the anti-electron, etc. Baryons are where the protons and the neutrons fall. And then there's another particle called a meson, which we don't, like, that's kind of the bunch of different kind of particles named with Greek words. Baryons and mesons are part of the hadron family. Yeah. I don't know, I don't suspect that this is stuff, like, I think that this is the stuff you really need to know. How do you proton and neutron and quarks, and that electrons aren't made of quarks. Electrons are as small as they can get, but you never know, so I'm including this stuff here. So leptons and baryons are also referred to together as fermions, and mesons are also part of bosons, which is interesting, because it goes back to that weak gauge boson, and I don't know how that relates at all. Okay. Yeah. Yep. I'm going to stop the video now. We'll do the questions together. But I don't think I'm going to do, well, we'll leave the video in there for that. Why not? Okay, you guys ready? This is just a few multiple choice numerical response practice questions that are fairly new, current kind of questions, like types of questions that you can expect on the diploma exam. The first set of 5 questions shows you 5 questions or 4 questions based on sort of the same idea, and it shows you what, like, a standard, like looking at the standard. So the 2 standards basically are acceptable standard, which is, oh, and I've got, like, it shows you the answers on here, so I forgot to take that off. My apologies for that. Just a couple of them have the answers. the acceptable standard is anything up like between 50 and 80%. So to be able to get between 50 and 80%, you need to be able to answer a question like this one. Intermediate is kind of falls in there. Like I'd put that intermediate at the 70 to 80%, and then standard of excellence, so over 80. Those are the questions that you need to be able to answer. So and that's just for the first 4 questions. The questions after that are just other practice questions. This particular set of 4 questions is based on Rutherford's gold foil experiment. And so you're given sort of the picture of the setup of the experiment in a context box. This is called a context box. Okay, and so you're given the setup for that particular question there. And so an acceptable standard question is to be able to fill in the blanks here. So this is a common kind of question where you have 2 blanks, and it's sort of a theory question where you've got 2 blanks, and you have to pick the appropriate stuff from the columns in the multiple choice. And theoretically, I've been told that, you know, like a huge part of the diploma exam should be able to be answered without having to do any calculations. Like, so 50% of your diploma exam is calculations, 50% is theory. And of those calculation questions, a large proportion of them you should be able to answer without your calculator, just by knowing physics. Okay? I'm not suggesting going in there and don't use your calculator at all, but you should at least be able to eliminate some of the answers if you don't know what to do. And that's kind of key, like when you get a question that you don't know how to answer, to be able to eliminate the ones that you know are wrong, or like at least get yourself down to like a 75% chance or a 50% chance, and usually you can eliminate at least 2. So in this one, it's just in Rutherford's experiment, illustrated above, the type of radiation directed toward the metal foil was 1, and so you want to pick either alpha or gamma, and then based on observations made using the detection screen, the atom contained either a small dense positively charged nucleus or electrons in stable circular orbits. So this has a lot to do with just knowledge of Rutherford. So now, if you didn't remember that it was alpha particles, the thing to remember there is no one in their right mind would do an experiment with gamma photons. Right? Well, yes, except for the Incredible Hulk, right? Because they're dangerous. Like alpha particles are as well, but they're not nearly as dangerous as gamma particles. So you should be able to eliminate C and D right off the bat by knowing that it's got to be alpha.
Yeah. Gamma just shoot right through it.
Yes. Well, there's another point there too. Gamma's not going to be deflected by anything. Yeah. Good point, Aaron. So then what you have to do is then the second part is based on what did he actually discover in his experiment. So did he expect, and it's kind of cheating because the answer's there, but did he discover small dense positive charged nucleus or electrons in stable circular orbits? Small dense positive nucleus, right? Who did this?
Thompson. Okay.
Bohr. This is about Rutherford. Yeah, Bohr did that one. Okay. So that's just like an example of how you can, if you know other things about the physics that are happening in a question, you can kind of eliminate some of your answers. So that's a standard, that's acceptable standard. The next one, I actually find this to be kind of a bit of a tough question. It's intermediate, but I find it a bit tough. So in Rutherford's experiment, the path of one of the particles, and notice it doesn't tell you alpha particle, right? But and the radiation beam was deflected as shown below. So there's our path, and we want to know which of those points the particle experiences the greatest electrostatic force. So it's being, it's encountering a nucleus somewhere here. So it's encountering the nucleus, which is full of protons. So which point on there? And I mean, the answer is on your sheet. It's not. On this one, it is. It's at R, because that's sort of where the greatest deflection really occurs. Like here, it's still going straight. Then here, it starts to encounter something that causes it to curve. And then this is just the path that it keeps taking once it's kind of curved away from that nucleus. So that's why R would be the answer there. But it's kind of tempting to say P or S, except that at S it's traveling straight, right? There's no curve. Now at R it's traveling straight, but it's the fact that it curved a little bit before R that makes that where it experiences the greatest electrostatic force. The next 2 questions are calculation-based, and they're considered standard of excellence, particularly because of the sheer number of calculations you have to do to get the answer. So use the following information to answer the next 2 questions. In the Rutherford alpha particle schedule, again, it says alpha particle, so these 4 questions wouldn't show up on the same test. Okay? Because you're never going to get 4 questions on the same concept. right? One question per concept basically is what you're gonna get. You've got 50 questions total, sorry. Not 50. Maybe it is 50, yeah, it is 50, science 30 to 20. It's 50 questions, it's 16 multiple, or 36 multiple choice and 14 numeric response. And there's more than 50 concepts that we covered in physics, so they have to kind of use the questions sparingly. In the Rutherford alpha particle scattering experiment, some alpha particles were detected coming straight back from the gold foil. When an alpha particle is emitted by the radium sample, it has a kinetic energy of 1.0 times 10 to the negative 12 joules. The electric potential energy of a charged particle in a radial electric field is modeled as EP equals K Q1 Q2 over R. Okay, so this is not a formula on your formula sheet or formula we talked about, so they give it to you and they tell you what it stands for. No, we didn't. Did we do questions on it?
Yeah. Oh.
We did Fe equals K Q1 Q2 over R squared. And that's what this is based on, because, your electric force is K Q1 Q2 over R squared, and force, right, is, energy, like, energy or work is force times distance, right? So then we can say that force is energy over distance. So then, instead of writing force here, you can write energy over distance, which then allows you to cancel one of the r's, and that's where that formula comes from. Okay, just equating that. You don't need to know that at all. Yeah, because if they give you a question like this, they're going to give you the formula. What we need to know is how to find the maximum acceleration of an alpha particle as closest approach to the nucleus of a gold atom from that. Okay, and this is a standard vector question. It's not that tough, it's just knowing where to go with that. And if you're asked to find acceleration, chances are what you want to use is F net over M, if that's going to give us acceleration. So we know our mass. So we know the mass because we're talking about an alpha particle. So we have a mass of 6.65 times 10 to the negative 27 kilograms. What we don't know is F net. So we need to find F net. And 27. Yeah, negative 5 kilograms. That's not your formula sheet. You guys should have that memorized. Okay. No. So now, the way to get F net is really going back and using this question here, or that formula there, that F net is energy over distance that it goes. And so if we find out, like, if it has, when the alpha particle is emitted by the radium sample, that's its kinetic energy. The electric potential energy of a charged particle in a radial electric field is modeled this way. So that, like, our kinetic energy here, by conservation of energy, our kinetic energy there basically is equal to our potential energy. So we can use this formula to find the distance. Then that plugs in there for the distance. We know the energy up there. And then we can do energy over distance that we found, and that will give us F net. So this is considered standard of excellence because there's really 3 calculations to get to where we're going, apart from understanding how to get there. So if we want to find R from that is K Q1 Q2 over E. So K times now. And here's the other thing with the charges. You've got an alpha particle. What is the thing that the alpha particle is encountering in here, in this question? What kind of nucleus? Gold. So then, okay, so the alpha particle is 3.20 times 10 to the negative 19 coulombs. The gold nucleus is full of protons. We need to know how many protons it has because that's how we find the charge of that gold nucleus. Okay, and it's got 72 protons, atomic number 72. And then if we divide that by 1.0 times 10 to the negative 12 joules, that will give us the distance. And what we're finding here basically is the distance that the force is applied over, which is like for the amount of work that's being done, which is represented by the energy amount that we have. So that's our distance. And I kind of run out of room. So this is indicative of, like, on the form or on the diploma, you're going to end up with, because force times distance of force is work over distance. You're going to end up with two numerical response questions at the end, 13 and 14, that are like this. It's basically, you're not given a lot of information, you're asked to find something, and you have to figure out the long process of how to find it. Then you have to tell them what physics principles you use to find that. Typically, about 13% of the people in the problems get this one right, and maybe, or sorry, about 30% of the people in problems get this one right, about 13% get this one. Sorry. I didn't think it would do that when oh, and I've got the movie playing too, isn't that great? I didn't think it'd do that when I have it on silent. That's for when I'm driving in my car. What's funny is if I can say a command to send a text message and it never gets it right. Ever. As last night I heard that one before and it sent it as something 24. Yeah. So back onto this really horrible stinky question. So if we want to find the force, we're going to take our work, which is the energy value that we were given to begin with, because basically through conservation of energy, that kinetic energy is equal to that potential energy, and then divide by the distance we found over which that energy, like that work is done, and that is going to give us a force of 27.5 newtons. So we can then take that force up here, 27.5 newtons, divided by the mass of an alpha particle, and that gives us an acceleration of 4.1 times 10 to the 27 meters per second squared. And part of this, I guess, like you know, if you have a question like this you don't know how to do not waste your time looking at it. You can mark it and go back to it at the end. And that's why they move these to the end of the diploma exam. So you used to be right smack in the middle or in the appropriate unit, and then people weren't finishing the diploma exam, and then of course they get like 40% because they hadn't finished. So they move them to the end, which is nice. These are the questions that they've added to try and address the testing, the things that the written response testing. So they added these types of questions when they dumped the written response. Part of this also is knowing how to put it into the boxes. So if you look here, we have a gold atom expressed in scientific notation, so the acceleration of the alpha particles, a decimal b times 10 to the cd. So this is A, this is B, this is C, and that's D. And what you put in the box then is A, B, C, D. So 4, 1, 2, 7. They usually key them if you've done if you've had a rounding issue, like if you didn't round correctly, like you put 4.0 and it's supposed to be 4.1, that would still usually be keyed as correct. Okay, because they don't want to mark it wrong because you did you read something off your calculator wrong when you've done all the math correctly. So then the two physics principles must be used to determine the maximum acceleration of an alpha particle. We want to use the numbers on the tariff sheet so that 0 through 9. And there's more than one right thing, but what I used was work energy. 3 was work energy. And then 1 is accelerated motion. And the order, they used to be really particular. It says with the order in which they were used, that's not necessarily true anymore because there's been some argument over that. So you would just write 3, 1 in that box. But in this particular question, they'd also accept 1, 3, they'd accept 5, 1, and 1, 5, which is conservation of energy and accelerated motion.
Well, you write 3, 1 there?
Yeah.
Right.
No, it's start in the left box. If you're going to have empty boxes, the empty boxes go on the right. Okay? Start on the left. Now, I've heard conflicting comments. I've heard that from Mr. Erickson said that they will still mark it right even if it's in the wrong box. I've heard that that's not true. But I do know that Mr. Offram once said to me that he goes through and kind of takes a look to make sure you've written it the right way. Okay? And then he'll kind of deal with that. Okay, so I'm going to do question 5 as well here. I'm going to skip this one for now. I think we'll go through that one at the next week just so I can give you guys a chance to get some work done and my video doesn't become like an hour long.
Okay.
So this is what the Bohr energy level, a particular atom emits a photon of wavelength. So if it emits, is it transitioning up or down? Down, yeah? So it's transitioning down. Good.
Wait, down is toward the nucleus?
Yeah, yeah, down is to the ground state. So this is a ground state. And we've got energy levels here. It needs more energy for here to be up here. And it needs less energy here. So these, the ones, like the ground state is usually a higher number, but it's negative, so it's actually a smaller number. Then the numbers get smaller, but they're negative, so they're actually getting bigger as you go up. So we have a particular atom emits a photon of wavelength 471 nanometers when one of its electrons undergoes a transition from one stable energy level to another. So, you know, it's going, maybe it's going from there to there. And we're told that the final energy level has an energy of negative 6.04 electron volts. We want to know the energy of the initial level. Like, so we want to know what that energy level is, like where it started. So we have the wavelength, right? So we have the wavelength, so we can use wavelength to find the energy emitted. Because that's equal to hc over lambda. We're in electron volts, everything's in electron volts, so use the electron volt version of Planck's constant. Why is that boring? It's really yawning. Yawning what? Means you're thinking, oh really? Okay, that's good, never mind, then I take it back. I'm happy I'm boring you. I kind of went into the next question. I didn't read quite enough room for this one. So I get that the energy emitted is 2.637 electron volts. So that means from going from here to there, 2.637 electron volts is emitted. So that means this energy level up here, that energy has to be negative 6.04 electron volts plus 2.637 electron volts. Because it like that's how much more energy it has, which gives you negative 3.40 electron volts. Now, you should be able to eliminate D, because if you know that it's transitioning down, then it can't possibly have less energy, like in the final, it can't have, you know, the initial where it started can't be smaller than where it ended. And where it started can't be the same as where it ended. So it's got to be one of those two. And notice that this one here is just finding that energy. That's where that answer came from, is just finding the energy emitted and not doing the second calculation. Did you do negative? Negative 6.04. Oh.
I did that, but then I ended up.
Oh, because it's 471 times 10 to the negative 9. If you do it as 4.71, it's got to be times 10 to the negative 7. Sorry, that's kind of, no, that's covered by the words there.
Give it right there.